Welcome to the central force problem. Today we are going to discuss the free body problem. Up until this point, we have mainly treated integrable problems for which the equations of motion can be integrated to give closed-form solutions. The main focus of this chapter has been on the inverse square law to body problem, leading to circular, elliptic, parabolic, and hyperbolic orbits. The first two are examples of closed orbits. Solutions can also be found for other force laws derived from power law potentials. In most cases, however, the equations of motion cannot be integrated. In particular, the Kepler problem for free bodies becomes much more complex. We are to consider free masses labeled by the numbers 1, 2, and 3, which are located at the radial vectors labeled by the same three numbers in the center of mass frame. Then we can write Newton's second law for the first body, for instance, in the form here. So it's just a gravitational interaction between the first body and the second body, and the first body and the third body. And obviously, the similar equations can be written for the other two acceleration vectors. Now, with the cyclic notation of the s vector of index I being equal with the difference between the radial vectors j and k, this set of vectors will obviously have the property that their sum cancels, is equal to 0. So it follows that we can write the Newton's second laws for these free bodies in a symmetrical form. So we can cast the system in the form of free equations for the s vectors, where the mass m is the sum of the masses of the free bodies, and the vector g is the sum of the s vectors divided by their cubes, and the cubes of their magnitudes, and multiplied with the Newton's gravitational constant. Now, the system we have obtained here has no general solution that is of any kind of practical importance in real-world applications, but it can be solved exactly in simple cases. One example is the Euler solution, which is a solution where the free bodies are always collinear and the bound state is given by confocal ellipses swept with the period tau. In the particular case where the g vector vanishes, this leads to a case of free decoupled equations, which together constitute a decoupled Kepler problem, for which the solution found by Laplace is that where the masses are located on the vertices of an equilateral triangle. There are also various asymptotic solutions. For example, in the case where the total energy is positive, all masses move away from each other, or one mass escapes, leaving the other two bound in an elliptical orbit. Even in the case of negative energy, one can once again find a solution where one of the masses escapes and the other two are left bound, or all three masses remain bound together. The restricted free body problem involves two large masses bound together, while the third one is relatively very light and just perturbs their motion. As an example, one can consider a spaceship moving between the Earth and the Moon, or the Sun perturbing the Moon's orbit. In the first case, the astronomical bodies are unperturbed, but the spaceship interacts with both through inverse square law forces. In general, satellite orbits at altitudes of roughly 150 kilometers above the Earth's surface are perturbed by the planet's non-spherical mass distribution. The potential of the Earth-Moon system resembles that of a point-like source only at very large distances. Otherwise, the equipotential surfaces encircle the two bodies separately, leading to emergence of the so-called Lagrange points. L1, L2, and L3 lie along the axis joining the two bodies, while L4 and L5 are placed symmetrically about the same axis. Point 2 is a saddle point. Points 1 and 3 are at a transition between orbits that encircle one of the bodies individually and orbits that encircle the pair, and the points 4 and 5 are minima that can bind masses in elliptical orbits. Assuming a restricted free-body Kepler problem with circular orbits for the heavy bodies about their center of mass, the Lagrangian of the light mass is given here. It is simply a kinetic term written in circular polar coordinates and a potential term which is time-dependent. Circular motion implies that the magnitude of the radius vector is constant and that the radius vector itself rotates with fixed frequency omega in the inertial frame. Going to a frame rotating with the same frequency, the two bodies appear at rest, and the new Lagrangian can be written through the transformation theta prime equals with theta plus omega and multiplied with the time. And the cylindrical coordinates given here, the Lagrangian can be recast immediately in the form below, or if we perform a few more simple calculations in the form given here, where the first term is the kinetic energy, and the last three terms represent the Coriolis, the centrifugal, and potential contributions with a potential that is now time independent. And we've already seen something similar to this in the previous chapter when we discussed the motion of a rotating mechanism as seen in the laboratory frame and in a frame attached to the mechanism. On deriving the Lagrange equations and by imposing that the generalized velocities vanish, so with these conditions which correspond to constant coordinates, one obtains the 5 Lagrange points. The behavior of small displacements around these points specifies their stability, and it turns out that only the points 4 and 5 are points of stable equilibrium. The Solar and Heliosphere Observatory, or SOHO, or the James Webb Space Telescope, are examples of spacecraft orbiting Lagrange points of the Sun-Earth system. In summary, we have described briefly the general statement of the Newtonian free body problem. We have mentioned exact and asymptotic solutions for particular simple cases, and we have explored the formulation of the restricted free body problem. In the following, we are going to discuss the kinematics of rigid body motion. So, with that being said, this chapter is concluded, and I will leave you with the words of Johannes Kepler. I believe they were written in a correspondence between Kepler and Galileo, though I am uncertain of the source, and and I'm also uncertain on the accuracy of the translation itself. But regardless, the words are quite beautiful and prophetic, and feel very fitting for the conclusion of these discussions. So, thank you very much for watching. I hope you found the video worth your time, and I will catch you later. Goodbye.